Question number 21. Figure shows the uniform square plate from which the part XBYA has been removed. If the moment of inertia of the plate around axis perpendicular to the plate through the points A, B and C are IA, IB and IC respectively, then you have to compare IA, IB and IC. There is a plane object. It is like this square shaped object, but this part has been removed. Then we can consider A, B, C points. We know that moment of inertia of an object around an axis is depending on mass of object and mass spreadness of object. Now, for ABC axis, there is the same mass because of there is the same object. We have to consider the same object. But when considering mass spreadness from A axis is the largest value because of masses has been spread to a long distance. Then when considering C, it is the second moment of inertia mass spreadness of object around C is less than A but greater than P. Then we can get IA, IC and IB is the correct order of mass spreadness. Then moment of inertia, order of moment of inertia IA, IC, IB. Then we can get IA, IC, IB. Answer is 4 for the question number 21. Then 22. One end of a thin non-elastic string of length L is attached to a small object mass M resting on a frictionless horizontal surface, and other end is fixed to a point on the surface of a vertical cylindrical pillar of radius r, so that the string remains horizontal. A velocity v is given to the object perpendicular to the string and along the surface as shown in the figure. The angular velocity of the object around axis of the pillar when it hits the pillar is. We have to consider angular velocity around the axis. We can consider that this is the circular shape of given cylinder, and the object is rotating around this cylinder. When rotating around this cylinder, the length of chord is decreasing with time and it is moving in a path like this. Radius is decreasing. Then for the final set situation, velocity is towards the center of cylinder. Then velocity is towards the center of cylinder. We know that omega equals V equals R omega. Tangential velocity equals to radius into angular velocity. Now we have to find the angular velocity. Then we know that tangential velocity is 0 for the final situation because of the velocity is towards the center. Therefore, this value is 0, then omega value also 0. Then angular velocity for the final situation should be 0. Answer is 1 for the question number 22. In question number 23, if the angular velocity of an object varies with time as shown in the figure, the corresponding variation of angular displacement theta with time is best represented by. We know that gradient of angular displacement time graph should be represented angular velocity. Now in given graph, angular velocity is increasing, therefore gradient of angular displacement time graph, theta time t graph, should be increased with time. Then answer should be 5 for the question number 23. 24. Two stars A and B of uniform densities have equal radii. Star A have twice mass of B, is spinning 3 times faster than B. The ratio angular momentum of star A to angular momentum of star B. I will consider A and B stars. Two stars A and B of uniform density have equal radius. Radius equal. There is the same radius. Star A having twice of mass of B. Then if the mass of A is 2m, mass of B is m. And B is spinning 3 times star B. Star A having twice of mass of B is spinning 3 times faster than B. Then A is spinning 3 times faster than B. It means angular velocity of A should be 3 omega if the angular velocity of B is omega. Now we have to consider the angular momentum. We know that angular momentum is I omega. I omega value of A divided by I omega value of B. It is the question. Now we know that I is depending, I is directly proportional to mr square. If it is a point mass around an external axis, we can get I equals mr square. But now we have to consider the rotating around axis on the object. Therefore, we have to use the constant value for this term. Therefore, we can get I directly proportional to mr square. Then we can get R is constant for both objects. Therefore, I is directly proportional to mass. Then we can get mass into mass 2m for the object A into angular velocity 3 omega divided by mass of B m into omega is the ratio between angular momentum. Then we can cancel out omega and m. 3 into 2 6. 6 is the answer. Then question answer is 4 for the question number 24. Then question number 25. A circular disc of radius 0.5 meters rolls with a uniform angular speed 12 radians per second on a horizontal surface without slipping. 2 points P and Q are located on the perimeter of disc. The speed of the 2 points relative to the earth when they are at the positions shown in the figure are. We know that tangential velocity of the object is r omega. Then we can get V equals r omega. Then tangential velocity is radius 0.5 into angular velocity 12. 0.5 times 12, 6 radians per second. Now we have to consider that when rolling object, it means there is a rotational motion and there is a linear motion. Rotational and linear motion is the rolling motion. This is the rolling object. Then for the rotational motion, we know that velocity for this point should be 6. It is r omega. This point should be 6. When the object is flipping, it means linear motion. There is a constant velocity for all points in the same direction, 6. Now, when rolling, we have to add these velocities. 6 plus 6, 12 for this point. There are opposite directions when considering this point. Then 6 minus 6, 0. Then velocity of P should be 12 and velocity of Q should be 0. 12, 0. Answer is 5 for the question number 25. Then question number 26. Is the moment of inertia of an uniform cylindrical rod about the axis ABC shown are IA, IB and IC respectively. Then we have to compare IA, IB and IC. Again we have to consider the same object, therefore mass is constant for all situations, A, B, C situations. But there is a different mass spreadness for A and B and C. Therefore we have to consider mass spreadness. The lowest mass spreadness could be observed for A along the axis A, and the highest mass spreadness could be observed for C. Then we can get moment of inertia IA, IB, IC. It is the order of moment of inertia IA, IB, IC. Then answer is true for the question number 26. Question number 27. A space shuttle B of moment of inertia I2 and angular speed omega 2 joins smoothly with the space station A of the moment of inertia I1 and angular speed omega 1. Along the common axis as shown in the figure, neglect the linear motion of both objects. The angular speed of the system about common axis after joining two objects should be. We have to use, there is a collision, we have to use conservation of angular momentum for a collision or explosion of a rotating object. Then we can use I1 omega 1, it is the angular momentum of A. There is an angular momentum for B in same direction, therefore we have got I2 omega 2. This is the total initial angular momentum. It means total angular momentum before the collision. After the collision, both objects are acting as a single object. Therefore, we have to consider total moment of inertia is I1 plus I2. Common angular velocity we can consider as omega. Then we have to find omega. I1 omega 1 plus I2 omega 2 divided by I1 plus I2. It is the total angular velocity after the collision. We can consider both one is the answer for question number 27. Then question number 28. The three uniform objects shown in figure have equal masses. Object A is a solid cylinder of radius r. Object B is a hollow cylinder of radius r. Object C is a solid tube whose sides are of length 2r. Is the moment of inertia of the object about the axis shown are IA, IB and IC respectively. Then we have to compare IA, IB and IC. We can consider the object B has the maximum mass spreadness because of there is a cavity near the axis and mass is in this region. Therefore, IB is the maximum value. Then we can compare IA and IC. IC should be, object C should be a cuboid like this. The cross section should be a square, and we know that this is the radius. When comparing cuboid and solid cylinder, we know that for the solid cylinder all masses have a maximum spreadness of r, but for this object we know that this mass is the distance from this mass to center is greater than r. Therefore, mass spreadness is greater value for C than A. Then next I value should be IC and minimum I value should be IA. Then we can get IB, IC and IA order. Answer is true for the question number 28. Then question number 29. The satellite is moving in elliptical orbit about the Earth. If the speed of satellite at point A is v, then its speed at point B will be. There is a problem with given diagram. The lengths are not given clearly. Therefore, I will explain by using some values. Sometimes the given answer will not be obtained because of there is a length difference. I will consider this is the Earth, this is the satellite. This distance is 4D and this distance is D. Now, we know that for a circular motion, we can use F equals ma towards the center. Now, centripetal force is given by the gravitational force. Gmm over r squared should be equals to mv squared over r. We can use centripetal acceleration v omega, omega squared r over v squared over r. Now, I have used v squared over r because of we have to compare the speed. Then we can cancel out 1 r term and m. By using this equation, we can get that v squared inversely proportional to radius. Then for this point, we can write v squared inversely proportional to radius is 2d. First equation. For the this point, we can consider velocity as v dash, v1, then v1 squared should be inversely proportional to radius is d divided by 2. D divided by 2. Now it is the second equation. We can divide both the equations. I will divide second equation and first equation. v1 squared divided by v squared equals to 2 over d. We have to divide by this value, multiply by reciprocal, 2d. Then we can subject v1. v1 should be equals to 2v. The answer should be 4 for the question number 29 according to my diagram. But they have not given correct distances. Then question number 30. A grain of sand is stuck to a tire of a vehicle at a distance r from its center. The radius of the tire is r. When the capital R, when the tire is rotating at angular speed omega, the sand grain detached suddenly from the tire. If the air resistance is neglected, the horizontal components of velocity of the grain relative to the vehicle immediately after detachment could have the value between. We can consider that when rotating tire, tangential velocity of sand, it is at the r distance from center. Therefore, rotating speed, angular velocity is given as omega, then tangential velocity of this sand particle should be r omega. R omega is depending the position, because of if it is at this position, velocity should be r omega when rotating tire in this direction, r omega to this direction. But if the sand particle is in this place, r omega to this direction, then we can get the r omega value, velocity value should be between minus r omega and r omega. Minus r omega and r omega. Then answer is 4 for the question number 30.